This presentation on hydraulic relief valves and pressure-reducing valves is the fourth in a series of 8 which provides a comprehensive introduction to hydraulics, the science of fluid under controlled pressure. I'm Paul Cook for Sperry Vickers. Pumps used in hydraulic systems are positive displacement units. This means that for every stroke, revolution, or cycle, they put out a fixed amount of oil. And that oil must have a place to go. If not, we're going to develop some exceedingly high pressures, which can rupture lines, blow out seals, and cause havoc with our system in general. To prevent such happenings, hydraulic systems must include pressure controls of some kind. We'll cover pressure relief valves and pressure reducing valves, two of the most common pressure controls. Let's start with the relief valve. In its simplest form, it doesn't have to be any more than a ball or poppet held on its seat by a spring. Here we would just tighten up on the spring until it was easier to move the cylinder with its required load than it would be to push the poppet off its seat. Oil, like all liquids, takes the course of least resistance. If the cylinder is overloaded or stalls, the increase in pressure overcomes the spring load on the poppet. The poppet is then lifted off its seat, permitting the pump delivery to go to tank at a safe level. Pretty simple, you say, and it is. But let's take a look at that spring. If the area of the poppet seat was only 1/4 of a square inch and we wanted a pressure setting of 1,000 psi, our spring force would have to be 250 pounds. Force equals pressure times area. That means it could support 1/8 of a ton without compressing, and that would have to be a very stiff spring. Now, let's go back to our circuit and assume we have a 1,000 psi setting on the valve and a gradually increasing load on our cylinder. When the pressure reaches 1,000 psi, nothing happens because the hydraulic force on the poppet is exactly equal to the spring load. Any further increase, no matter how little, unseats the poppet and a very small quantity of oil begins to flow through. This is called the cracking pressure because the valve is not yet open enough to pass the full pump delivery. The more oil we push through the valve, the wider our opening must become, and, of course, the more we must compress the heavy spring. And that, in turn, is going to take more pressure. Now, if our pump were a small one, say 1 or 2 gallons per minute, the increase in pressure would probably be negligible. 15, maybe 25 psi. A 10-gallon pump at the same spring setting, however, might require an increase of 150 to 200 psi to pass its full delivery through the valve. This difference between the cracking pressure of a relief valve and the pressure at which it can pass the full pump delivery is called override. A simple relief valve has too much override to be used in most of today's high-pressure circuits. One suggestion might be a larger valve, but then we'd have more area under pressure, and this would require an even heavier spring, so you can't gain that way. Fortunately, there are better valves for handling large quantities of oil. They have a number of different names. We call ours a balanced piston relief valve for reasons that will become obvious if we look at an illustration. We start with a piston which has equal areas on the top and bottom. It fits into a body which has a straight-through passage for convenience in piping and a port at the bottom which must be open to tank. If, for instance, our pump were on the left, oil would flow into the valve around the bottom of the piston and out the other side to the cylinder. Even a light load on the cylinder would cause sufficient pressure on the underside of the piston to lift it off its seat and permit all the oil to go to tank. To prevent that from happening, we install a spring on top of the piston, not a heavy one as we did before, but one so light that only 20 psi under the piston would cause it to lift. Next, we drill a small hole through the piston, connecting the area on top with the area on the bottom. Now, any pressure on the underside of the piston would force oil through the little hole into the top chamber until it was filled. Then, of course, the flow would stop. Now, let's go back to one of our basic hydraulic principles. To have flow through an orifice, there must be a difference in pressure. If there's no flow, the pressures will equalize. And once our top chamber is filled, the flow stops, and the pressures top and bottom become the same. With equal pressures acting on equal areas, our piston is in hydraulic balance, and the light spring holds it closed. What we've done is use a light spring and hydraulic pressure to hold the valve closed, instead of just a heavy spring. The rest is easy. All we have to do now is limit how high the pressure can go in the upper chamber. To do that, we put a small poppet with an adjustable spring in the top cover and a passage connecting it to the chamber above the piston. If we set the poppet to open at 500 psi, the pressure above the balanced piston will be limited to 500 psi. With 500 psi and our light spring holding it closed, the most pressure we can get in the bottom will be 520 psi. To increase or decrease the pressure setting, we merely adjust the spring in the cover. Actually, 3 springs are available, giving us maximum pressure settings of 1,000, 2,000, or 3,000 psi. You're probably thinking, that's a neat valve, and I can see how it works. But how does it overcome the override problem of the simple relief valve? Well, you're on the right track. To explain, let's use a 1 gallon per minute pump and set our valve at 1,000 psi. As the load increases, pressure rises until it reaches the setting of the poppet and pushes it off its seat. The oil wants to flow through the poppet and back to tank, but it can't all get through the balance hole. So the pressure beneath the piston continues to rise. When this pressure increases by 20 psi, it overcomes our light spring and lifts the piston off its seat. That 20 psi difference pushes about 1/2 gallons per minute through the balance hole and over the control poppet in the top cover. The rest of the fluid lifts the large piston off its seat and flows out the tank port. Now, a larger pump flow needs a larger opening, and our balanced piston must move up farther. In this case, though, it's only compressing the light spring, so the override is considerably less than what is developed in a simple spring-loaded relief valve under the same conditions. Perhaps this would be a good time to compare the actual hardware. This valve has 1/4-inch pipe ports and is rated at only 3 gallons per minute. Yet, look at the size of the spring it requires. Now, this one here is the balanced piston type. It has 3/4-inch porting and is rated at 45 gallons per minute, and due to its balanced design, requires only this light spring. Some difference. This 3/8-inch port in the cover enables us to remove and replace the seat for the control poppet. You must be sure to replace the plug when you're through. Leaving the plug out would be like opening the passage. There wouldn't be a flood because all the oil that would come out is what 20 psi could push through the little balance hole. The point is, you wouldn't have any pressure above the balanced piston, and it would open, limiting pressure in the entire system to about 20 psi. Now, no one would deliberately leave the plug out, but it is common practice to pipe a line from this port to a small off-on valve, which could be opened during periods of idleness. This is done to unload the system and save energy. We call that venting the relief valve. Sometimes, too, instead of an on-off valve, a spring-loaded poppet, like the one in the cover, is used to permit adjusting the pressure from a remote position, such as an operator's console. Remember, the maximum pressure adjustment in the cover can never be exceeded from the remote position. If it hasn't been stated in so many words, I think we can see that the primary function of a relief valve is to limit maximum system pressure, to control the force of the cylinder, or to control the torque of a hydraulic motor. Occasionally, it may need an assist from another valve to get the job done. Let's assume we have a circuit with two clamp cylinders, one larger than the other. The larger clamp cylinder requires less pressure than the smaller. Here we have a pump, two cylinders, and a main system relief valve. Anytime the pressure exceeds the spring setting, the valve opens, permitting oil to flow through the valve and out to tank. If the pressure drops, the spring forces the valve closed, its original position. Let's say our large clamp cylinder pressure must not exceed 500 psi, but a full 1000 psi is required by the small clamp. If we set the relief valve to limit the entire system to 1000 psi, that should take care of our small clamp, but it will be too high for the large clamp. Putting another relief valve set at 500 psi here would at first glance seem to solve that problem. But wait a minute. When this relief valve opens, it would limit the whole system to 500 psi. Remember, a relief valve is normally closed and opens when pressure reaches its setting. What we need here is a valve that is normally open, but closes when its setting is reached. Oil can flow straight through from inlet to outlet and into our large clamp cylinder because the spring holds it open. This time, though, we will sense pressure at the outlet port and let it oppose the spring. Now, anytime pressure at the outlet tries to exceed the spring setting, the valve closes and limits the pressure in the cylinder. If the spring were set at 500 psi, the large clamp cylinder pressure could not exceed 500 psi. Pump flow would still be available to the small clamp right up to the main system relief valve setting of 1000 psi. You've probably already guessed this valve is called a pressure-reducing valve, because regardless of how high the system pressure may be, it reduces the pressure in its portion of the circuit to its adjusted setting. A more realistic view of a pressure-reducing valve would look like this. A sliding spool fits into a body that has a straight-through port which never closes. High-pressure fluid can enter or leave through either side. A relatively light spring holds the spool down and open to permit oil to flow freely through the bottom or low-pressure port. Pressure from the low-pressure side is sensed under the spool to oppose the spring. However, like the relief valve, our spool has a balance hole from top to bottom, so pressures above and below the spool are equal. Here, too, a small poppet and adjustable spring in the top cover limit pressure above the valve spool. When the pressure under the spool exceeds the adjusted setting, plus the light spring force on top, the spool moves up, tending to shut off the low-pressure port. Actually, whenever the valve is under control, there is a small quantity of oil flowing up through the balance hole and over the small poppet. Since there is no tank port or pressure-reducing valve, this so-called control oil must be drained to tank through a small port in the top cover. Here we have a pressure-reducing valve cut away, so we can see the sliding spool and the light spring which holds it open. The sensing passages we discussed are actually small holes drilled into the spool, one of which lets oil flow into the top cover where pressure is limited by this small poppet and spring. This hump on the back contains a check valve to permit reverse flow, if, for instance, we wanted to retract our cylinder. Okay, now for a quick review. The functions of a relief valve and a pressure-reducing valve are similar. but there are some important differences. The relief valve is normally closed and opens up to limit the maximum pressure in the entire system, and it's drained internally. The reducing valve is normally open, and it closes to limit pressure in a branch circuit. It may contain a check valve for reverse flow, and it must be drained externally. Well, this wraps up Chapter 4 in our 8-part series on basic hydraulic principles. With the information put forth in this presentation, coupled with your own practical experience, you now have a strong fundamental understanding of relief and pressure-reducing valves. I'm Paul Cook for Sperry Vickers.